All right, so before we go into the new stuff, let's just review kind of what we know already. If I put a positive charge here at this positive plate, this positive charge has potential energy. You let that charge go, what would happen to the charge? The positive charge would accelerate over to the negative plate, and that potential energy would now be into what form? Kinetic energy. And assuming no friction in between, those energies are equal. So this whole chapter is about the energy of charges. The first term, which we looked at in a previous lecture, is V. Now, this symbol V is referred to as electric potential. V by itself is electric potential, and the definition for it is potential energy per charge. Okay? Electric potential refers to a point. So say, for example, I told you that the electric potential at this positive plate, right on the positive plate, we'll say the electric potential is 20 volts. So what is that telling you? That's telling you, well, what is a volt? Oh, what is volt? I didn't mention that yet. What do we measure energy in? Joules. What do we measure charge in? Coulomb. A joule per coulomb is referred to as a volt. So what would 20 volts be? That would be 20 joules of what? Potential energy per coulomb. Okay? Now, do you care? Is it helpful to know what the electric potential is at a single point? Not really. Like knowing that the positive plate is at 20 volts, you're not going to be able to do much with that. The thing that's going to be important is knowing the difference in potential between 2 points. So say, for example, the negative plate right here, let's say that that's at 5 volts. What would 5 volts mean? That means 5 joules of potential energy per coulomb. So what would be the important thing in this situation? 20 volts and 5 volts. The important thing there would be what? The change in potential, or the potential difference, is what? 15. And technically that'd be negative 15. Why would it be negative? Well, where does the electric field end? The electric field ends where? At 5. Where did it start? At 20. So you're going 5 minus 20. It's always final minus initial. Okay? So delta V, which is potential difference, would be change of potential energy per charge. So this equation here, it's key. One thing you have to be aware of, you need to know that electric potential is higher as you go up the electric field. So notice how I set up this previous example, 20 volts and 5 volts. The positive plate will always be at a higher potential than the negative plate. Now, what's the reason for that? Well, look, here's our definition for electric potential. If you take a little positive guy, and remember, everything in physics is based on little positive. If you take this little positive guy and you start moving him this way, what type of energy is he gaining? Potential energy. It's just like taking an object and moving it up the gravitational field. So look, if potential energy goes up for a little positive guy, that means the electric potential goes up. If this increases, then that increases. Does that make sense? Everything is based on little positive. Where does the little positive guy have more potential energy? The little positive guy would have more potential energy over here, which means that electric potential is higher at the positive plate. Okay? Now, this equation here, so this is new material, this equation can only be used when the electric field is constant. And where's the only time electric field is constant? When you're between oppositely charged parallel plates. So if I told you that this electric field were 100 Newton per Coulomb, the electric field there, everywhere in there, the electric field is the same. Now, what's the other situation where the electric field is not constant? It'd be a point charge. like this. We got a big charge like that with the electric field going out. Would this electric field remain constant? Because what happens as you move away from the point charge? The electric field gets weaker. All right, so it's not a constant electric field, and we'll talk about that in a minute. So if you do have a situation where the electric field remains constant, then this is the equation. This is the equation that applies, okay? But it can only be used with a constant electric field. Do not use this equation if you have a point charge, all right? Look at, technically there's a negative here. What I want you to do is take that negative and ignore it, okay? Now, why is the negative technically there? Well, it goes back to what I was just saying. If this is 20 volts and this is 5 volts, what would the delta V here technically be? Negative 15, because where does the electric field end? It ends on 5, started on 20, so it'd be a negative change. As long as you know that up the electric field is higher potential than down the electric field, as long as you know where the electric potential should be higher, you can ignore the negative. Okay? So basically, here's how you use the equation. Say I told you that this electric field is 100 newtons per coulomb, and the distance between the plates is 0.3 meters. All right, so you'd go, okay, the potential difference between the plates, electric field is 100 newton per coulomb, and the distance between the plates is 0.3 meters. So anybody remember what a newton times a meter is? What do we get if you multiply newton times a meter? A joule. So this comes out as 30 joules per coulomb. And then what do we call joules per coulomb? Volts. And technically, again, it's negative because in this situation, if the potential difference between the plates is 30 volts, it would be something like this. 30 volt, 0 volt. It's the change. And it would be negative because where does the electric field end? It's ending on smaller volts and starting on higher volts. Okay? All right, so let's look at an example. Okay, so here we have a problem. Questions 1 and 2 are very easy. Questions 1 and 2, you should be able to solve that in like a minute for both. All you're doing is you're using this equation for parallel plates. The answer to number 1 comes out as 20 volts, technically negative. The answer for number 2 comes out as 10 volts. Now question 3 is where you got to think. What question 3 says is if you put a proton at the positive plate and release it, what would be the velocity of the proton as it crashes into the negative plate? What would be the velocity of the proton? To answer this, you have to have some information about the proton. So I'm going to give it to you. The mass of a proton is 1.67 times 10 to the negative 27. The charge of a proton is 1.6 times 10 to the negative 19. So you need that info. All right, so take about 5 or 10 minutes. On the answer to number 3, just so you know, you can check your work, comes out at about 62,000 meters per second. Okay, I rounded that up. Okay, so here are the answers. We'll go over them. 20 volts is the answer to number 1, 10 volts number 2, 62,000 is the answer to number 3. Actually, before I solve this, I want to point something out. You're going to notice in chapter 16 that the unit for electric field is given as volts per meter. So see up here I have 100 Newton per coulomb, which is identical to a volt per meter. So why are they identical? Let me just show you. Newton per coulomb is identical to volt per meter. Let's just look why. Well, what's a volt? A volt is a what? A joule per coulomb per meter, but what's a joule? A joule is it could also be called a Newton times a meter. And then what cancels there? The meters cancel. Newton per coulomb. So a Newton per coulomb is the same as a volt per meter. So chapter 15, when we were doing forces, Newton is force. So like, look, 100 Newton per coulomb, what does that mean? If you stuck a charge in here, and that charge happened to be 1 coulomb, how much force would the electric field give the charge? 100 newtons. What if it were 2 coulombs? Then 200 newtons. What if it were 3 coulombs? 300 newtons. All I'm doing is using F equals QE, right? mg QE. All right, now volt per meter. If we say the electric field is 100 volt per meter, what we're saying is the potential difference is going to be 100 volts for every meter that you move in the electric field. So for example, if these parallel plates here, if this distance of separation were 1 meter, how many volts would be across these plates? 100 volts. What if the distance of separation were 2 meters? Then 200 volts, right? What if the distance were 3? Then 300 volts. The potential difference would be 300. All right, so volt per meter, you're going to see that as the electric field in chapter 16. All right, so let's go through the solutions. So number 1, we're using this equation. Forget about this negative. As long as you know the positive plate is at higher volts, you're fine. So we're going E times delta X. So the electric field is 100 volts per meter. What distance separates the plates? 0.2. So that gives 20 volts. And that's the change. So you could say 20 volt and 0 volt, or you could say 100 volt and 80 volt. What do those have in common? The change is 20, right? You don't really care what the electric potential is at a point. The thing that you care about is the change from one point to the next. Okay. Number 2, you're plugging into the same equation. We'll just do right here. Instead of 0.2, you're told that the distance between A and B, this distance in here is 0.1 meters. So just change the 0.2 to 1. So how many volts are there between points A and B? Maybe 10. That make sense? So point A, for example, 10 volt, point B, 0. The change would be 10. Or you could say 100 volt and 90 volt. It's the difference between the 2 points. All right, number 3 is the trickiest part. Okay, so we have a proton. This proton starts here, and we release it from rest, and it travels to the negative plate. So what type of energy does the proton start with? It starts with potential. What type of energy does it end with? Kinetic. Now, what do we know about this point to that point? What did we calculate in number 1? From those 2 points, the voltage is 20 volts. Technically negative, right? Why is it technically negative? Well, because where does the proton end? The proton ends on lower volts. Where did it start? On higher volts. So it's technically negative. So now what we do is we use the definition for voltage. The basic definition is that. So we can figure out the change in potential energy for the proton as it moves from positive plate to negative plate. So this is negative 20 joules per coulomb. A volt is a joule per coulomb. And then the charge of a proton is 1.6 times 10 to the negative 19 coulombs. The coulombs cancel, and we get a change of potential energy equal to negative 3.2 times 10 to the negative 18. That's how much potential energy the proton lost. Now, the loss of potential energy is equal to the gain of kinetic. Remember, this starting potential is equal to the ending kinetic, right? The loss of potential energy equals the gain of kinetic. So how much kinetic energy, let me put it this way, what's the change of kinetic energy of the proton? as it moves from positive plate to negative plate? It's the same as the loss of potential, right? What's change of kinetic? Change of kinetic is going to be kinetic final minus kinetic initial. Well, if the proton started at rest, what's the initial kinetic? 0. So the change of kinetic is equal to the kinetic final. So you go, okay, kinetic, what's the equation? 1/2 mv squared. So velocity is going to be 2 times kinetic energy over m, and then we plug into that. So this is going to be square root 2 times 3.2 times 10 to the negative 18 over 1.67 times 10 to the negative 47. That's the mass of a proton. So when you plug in, you get an answer of 62,000 meters per second. Okay? Okay. Any questions on this problem? All right, moving on. Unfortunately, we're not done. Okay, now, what I've talked about so far has been if the electric field is constant. What if the electric field is not constant, like in this situation here? The electric field gets weaker, weaker, weaker. Well, what you have to do in a situation like this is calculate what the electric potential is at a point away from the big guy. So say that this big guy is Q. If you travel a distance r from the big guy, you can calculate the electric potential. So here, V is electric potential. It's going to be KQ over R. Now, who remembers from last chapter, there was a very similar equation from last chapter. KQ over R squared. This is for finding electric field. This is for finding electric potential. So if you wanted the potential difference between 2 points for a situation like this, what you would have to do is find the electric potential there, and then go to the other point, find the electric potential there, right? If you knew the electric potential at each of those points, just subtract them, and you have the change of potential, right? That's how you would have to do it like that. Okay, look. Electric fields. Guys, electric fields, scalar or vector? Vector. So look, this is vector. Electric fields are vector. Electric potential is scalar. Okay, now why is that? What is electric field? What's the basic definition of electric field? The basic definition of electric field is force per charge. Is force vector or scalar? It's vector because it has direction. If you talk about a force, you know, a force is a push or a pull. Forces have direction, which means that electric fields are vector because forces are vector. Now, what's the basic definition of electric potential? The basic definition for electric potential is energy per charge. Does energy have a direction? So say you ate 500 calories for breakfast. Calories is energy. Could you say, I ate 500 calories north? Can you put a direction on energy? No, which is why electric potential is scalar, electric fields are vector. So what does this mean? It means, okay, so let's go to the next screen. When you have a situation like this is our last screen, then we're done. So if you have a situation like this, so here you have 3 charges at the corners of a rectangle. What this question wants you to do is find the electric potential V at that corner, okay? Is this going to be a big old hassle to do? Because electric potential is scalar. What do you do with quantities that are scalar? All you have to do is literally just add them up and you're done. Okay, so how are you going to go about this? Well, let's call this charge here number 1. This will be charge 2. This will be charge 3. So you're going to go like this. Here's the equation for finding electric potential. You're going to go KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. Like that. Plug it in, you're done. But I want to draw your attention to one thing. Notice here that the Q is not absolute valued, which means, see this guy right here? Charge number 2, you got to plug in negative. You got to make him negative. He's not absolute valued. But it's easy compared to, so last chapter, what would the question have been? Last chapter, this would have been find the electric, not potential, but what? Field. Ooh, that's a lot harder. Why is that a lot harder? Because that's vector. So remember, here's how you do that. Here's charge 1, here's charge 2, here's charge 3. Okay, what's the electric field doing at this point from charge 1? Like that, E1. Why is that? Look at it goes out in all directions. Out, out, out like that. So it goes out like that, right? Okay, charge 2, negative, in, like that. So it's going like this. Boom, there's the electric field from charge 2. And then charge 3, the electric field's going like that. So then what you would do next is you would go, okay, E is KQ over R squared. You have to find out what each of these electric fields are, but then your work has only begun. The work has only begun, because then what do you do after that? You got to break everything into what? X, Y, put them tip to tail, do Pythagorean theorem. Vectors are a pain in the booty. Big time. So what's the good news in all of this? I mean, chapter 16 is kind of dry, and it is kind of not the most exciting chapter there ever was. But what's the good news here? If you're asked to find electric potential, you're like this. Ooh, electric potential is all about energy. Energy is scalar, which means all I have to do, add it up, dude. Just go V1 plus V2 plus V3, done. It's easy. It's much easier. It's not vector. It's scalar. All right, we're done. We'll start here tomorrow.